So hello students, today I am going to complete this lecture on the Dirac delta potential, and in the previous lecture we studied about the bound states, the free scattering states that are occurring in this potential or in any potential, and we also studied the significance of the bound states and the scattering states. The non-normalizable functions, they are not only it is not that they are not significant, they have their own significance. This Dirac delta potential is of special significance in the sense that here the potential is infinite. Now how to deal with this situation? So in the last lecture what we did, we used these boundary conditions and solved the Schrodinger equations. This is for the case when energy is less than energy of the body, it is less than the potential, it is negative, the energy is negative, minus. So what will be the solution? We observe this. I will tell you what state does it describe, and we were discussing the form of the Schrodinger equation. In the left of x equal to 0, and at x equal to 0 we have a continuity which is a potential infinite. This is x negative, this is x positive. So this is the condition where the energy is negative. We are solving the Schrodinger equation, and let us see where this solution takes us. So we are in the left of the region, left of the origin, Vx is equal to 0, and we have obtained our solution. Partly the solution that f is equal to b when we are applying the boundary conditions. This is the first boundary condition, says first condition of well-behaved wave function, that psi must be continuous at x equal to 0 or at the point of discontinuity. So if you put in these two equations x equal to 0 and equate these two equations, what you are getting? You are getting f is equal to b. Now let us come to the second condition. The second condition of well-behaved wave function says that d psi by dx must be continuous at x equal to 0. Must be continuous at x equal to 0. This is the second condition of well-behaved wave functions, x equal to 0 or at the point of discontinuity. Now you must have studied the concept of continuity and differentiability in the differential calculus, and that is the simple principle we are going to use at the point of discontinuity. So this is the principle we are going to use. Now this every condition that it is must be continuous at 0, d psi by dx must be continuous, and then you have this condition as psi x must be finite, single valued. All these conditions are related to some physical aspect, they have some physical significance. We need to understand what is the physical significance. Now this second derivative in this condition is not going to give us any very important physical condition, and we will see why it is so. So in this case, when you are studying the Dirac delta function, Dirac delta potential, the important thing is that the continuity of the derivative of the wave function, it has to be understood in a particular manner, it has to be deeply understood. And here we will see what is the effect of a potential what is infinite, that is infinite. The importance of Dirac delta function or potential shows what is the effect of an infinite potential. Infinite potential. In the earlier cases, we did not have this kind of situation where the potential is suddenly increasing in the form of a spike and it is infinity. So let us try to understand. Now the second condition, that d psi by dx should be continuous. It is not going to produce any physically acceptable, or you can say useful result. Why it is so? Why it is so? The question is why the continuity of d psi by dx, continuity of d psi by dx is not going to be useful. Not going to be useful. To understand this, let us see what is happening. The important aspect is that at the point of discontinuity, if this is x equal to 0, suddenly there is a sharp increase in potential and this is going to infinity. This is negative, this is positive. So this situation is similar to a situation where you have a straight wire and suddenly there is a kink or a turn in the wire. This is the kink. In many of the experiments of electrical part, you must have seen that it is a precaution that the wire you are using, it should not have some kink. So what is happening here is that we have a straight wire and suddenly it has a turn. All of a sudden it has a turn. Now whatever is flowing in this direction faces a discontinuity at this point. This is the physical meaning, discontinuity. So the situation is similar. Situation is similar to that of a straight wire, that has a kink or turn at one point. This kink is a discontinuity. This kink is a discontinuity. This is the thing that is happening here in the potential case. So what we have to do here? What we need to do here? So at x equal to 0, the delta function, delta potential is similar to a kink in the wire. Now we need to understand why this condition should hold and why this condition is required. The continuity of d psi by dx, the continuity of d psi by dx is useful to integrate the Schrodinger equation. Then only you are going to get the wave function and extract information regarding the particle. Integrate the wave function from minus epsilon, say, to plus epsilon with limit epsilon tending to 0. So what does this mean? You are integrating the Schrodinger equation minus h bar square by 2m d2 psi upon dx square plus vx psi x is equal to e psi x. You are going to integrate this equation between minus epsilon to plus epsilon. In the limit epsilon tending to 0 means the region of interest is shrinking. It is becoming narrow. This is the idea here. So if we integrate the equation, we will get something like this. This part is nothing but, if you integrate it, it is d psi by dx. D psi by dx. Then you have this potential, integral of the potential minus infinity. I am coming to this integral. And this one is e psi minus infinity to plus infinity psi x by dx. Now what is the difference between other potentials and Dirac delta potential? The difference is that in general, let me put this minus h bar square by 2m here. What is the, if someone asks that what is the difference, between the Dirac delta and other forms of potential and other potentials. Other potential means the square well or symmetric square well, anything. It can be anything, any potential. The difference is that in the ordinary situations, what happens that this quantity on the right hand side, it becomes zero. It becomes zero. This is the condition at ordinary situations, at the normal situations. The last integral is 0 in the limit epsilon tending to 0. So let us put this integral 0. So this, in ordinary situations, or first let me write it like this. Let me write the equation. Minus h bar square by 2m minus epsilon to plus epsilon d2 psi dx square dx plus integral minus epsilon plus epsilon vx psi x. In most of the situations, this one is 0. This is perhaps equation number 6. No, 7. Whatever it is. This one is 0. So what you get is minus h bar square by 2m minus infinity to plus infinity d2 psi by dx square dx is equal to minus of minus infinity minus epsilon to plus epsilon vx psi x dx. This right hand side equation is 0 because we are taking the limit epsilon tending to 0, so it is a region of very small width. What happens in ordinary situations, ordinary means different from Dirac delta potential. Ordinary situations, what happens that the integral minus epsilon to plus epsilon vx psi x dx is equal to 0. But in the case of Dirac delta potential, the effect of potential is that this condition in this integral in the limit epsilon tending to 0 is not 0, because we have seen the form of this potential, that at x equal to 0 it is infinite, elsewhere it is 0. In the case of in the normal situation, normal potentials, normal I am saying different from Dirac delta potential, Dirac delta, the above integral is 0. The above integral is 0. So what is the consequence? The consequence is that consequence is minus h bar square by 2m, and it is showing that the integral on the left hand side, this one I am talking about, this one, this is simply the change in d psi by dx. D psi by dx, try to remember your class 11 concept. Dy by dx is the tangent. Continuity means the tangent should remain same. Tangent should remain same means dy by dx is equal to 0. This is how you find the tangent to a curve. This is the principle. It is not something which is very difficult. This is the principle of differential calculus when you are studying in standard 11 or 12. This is the concept. So consequence is that this is 0 in normal conditions. In normal conditions. And what happens? Your tangent does not break. The tangent remains same. There is no change in the tangent, and d psi by dx is continuous. This is the result. But if you have a Dirac delta potential, but in case of Dirac delta potential, minus h bar square by 2m, change in the d psi by dx or change in the tangent is not equal to 0. Rather it is minus alpha del x. Sorry. Rather this equation, this quantity is minus the form of the potential minus alpha del x or minus alpha minus epsilon to plus and epsilon Vx psi x dx. Remember the form of potential, it is minus alpha del x. This is the Dirac delta potential. So this alpha is here. So this quantity, as I told you in the previous lecture, minus infinity to plus infinity, if you are integrating this, this is not equal to 0 but equal to 1. So this is minus alpha. So this quantity becomes minus h bar square by 2m. Change in the tangent d psi by dx is equal to minus alpha. Minus minus cancel. So change in d psi by dx is a non-zero quantity 2m alpha by h bar square. Okay, so this is 2m bar by h bar square. This is the significance. So in Dirac delta potential, change in the tangent d psi by dx is not equal to 0 but it is equal to 2m alpha by h bar square, and it was negative, so it is minus because Vx was minus alpha del x, so it is minus psi 0. Psi 0 at point 0 it is going to infinity. So this continuity condition is changing in the case of Dirac delta potential. Now what we have psi x in our equation as b e to the power minus kx for x less than 0, sorry, plus kx for x less than 0, and f e to the power minus kx for x greater than 0. Now let us evaluate d psi by dx in these two regions. D psi by dx in x greater than 0, it will be equal to minus kf e to the power minus kx d psi by dx in x less than 0, it will be equal to b k e to the power plus kx. Put x equal to 0 and equate. Put x equal to 0. So not equate because they are not equal. So what you have, d psi by dx in x greater than 0 is equal to minus kf, and in x less than 0 it is equal to bk. So this is the condition we have. D psi by dx, for your simplicity, d psi by dx are different in x greater than 0 and in x less than 0. There is difference. It is not same. So this is the situation which is different, which makes it different from the ordinary potentials. Now what we observed, that the change in the wave function, change in the derivative is equal to minus 2m alpha by h bar square. Now using this we can find out the value of k. By using this we can find out the value of k. How we can do that? We have seen in the last lecture that f is equal to b. So these equations, we can use this, and d psi by dx in x greater than 0, that was minus kf, we can write it minus bf, and d psi by dx in x less than 0 is bf. So the change in d psi by dx is equal to bf minus bf is equal to 2bf, and this is equal to 2bf is equal to 2m alpha by h bar square. So this 2 cancel, or you can write, since this is, just wait a minute, from this we can write k is equal to m alpha by h bar square. So we can evaluate this k. This bf is k because we have b is equal to f. Let me correct it here. This is b, and it is not f, sorry. So this b is, so this one is equal to k, and our k is m alpha upon h bar square. So now we have evaluated k, and from k we can find the allowed energy levels, because k was minus 2me upon h bar square. See the last lecture. So k square is minus 2me upon h bar square. So E is h bar square k square minus 2m. Can you relate this equation? If you can relate, then it is very good. So, and we have what we have found, E is equal to, putting the value of k, it is minus m alpha by h bar square, sorry, 2h bar square. So this is the value of E that we are getting. Now what is the significance of this value of E? Minus m alpha square by 2h bar square. There is no n, as we have seen in the case of free particle in an infinite square hole. There is a n. Index, there is no index. So what you can see that there is, if there is no n, then it means that quantization is not there. We cannot identify the energy states by the index, is not there. This is not present. Now if you normalize the wave function that you have obtained, normalizing this, you can do it by yourself, or I am doing it for you. Minus infinity plus infinity mod of psi x square dx. This is equal to, because the coefficients are same, 2 mod of b square minus infinity to plus infinity. Sorry, it is 0 to infinity because we have changed the limit. E to the power minus 2kx dx. If you integrate it, you can easily find out what will be the result. B will be equal to root under k. So B is equal to root under k. So what is the result of our wave function? What is the wave function? So in Dirac delta, potential, the wave function in x less than 0 with energy less than 0, or for the time being remove it, in the x less than 0, the wave function is psi x. After normalization, what you are getting, it is root under m alpha by h bar e to the power minus kx, sorry, e to the power minus alpha x, e to the power minus alpha x by h bar square. This is the wave function. And energy, it is minus m alpha square upon 2 h bar square. So these are our results. Now what does this result mean? It is not over that you have obtained the calculations. What does this result mean? I am writing it here again. Psi x is root under m alpha by h bar e to the power minus alpha x by h bar square, and energy is minus m alpha square by 2h bar square. First thing, energy is negative, E is less than 0. That is why I omitted in the heading. This means it is a bound state. This means it is a bound state. And there is no n. This means for any delta function well, because it is a negative, I am explaining what is well. There is only one bound state. There is only one bound state, since Vx is equal to minus del x, alpha shows the strength of the potential, how strong it is, shows the strength of the potential, how strong the potential is. So for any value of alpha, any strength of the potential, in x less than 0, the physical condition is that there is only one bound state. There is only one bound state. So if you are asked, so show that in the x negative for Dirac delta potential, there is only one bound state, you can show it this way. Now why it is a well? Because our potential was Vx minus alpha del x. So this is a situation in the negative x-axis, in the negative direction, minus alpha. So we are considering this as a delta function well. This is the condition of a delta function well. So diagrammatically you can see the bound state wave functions for Dirac delta potential. They are given something like this. The exponential solutions are this type of solutions. So this is a Dirac delta potential well, because we have Vx minus alpha del x. So this is showing a potential. It is a potential well, Dirac delta potential well. We will discuss the case when Vx is plus alpha dx. So the conclusion is that for any strength of the Dirac delta potential, for any strength of Dirac delta potential, there is only one bound state. There is only one bound state. This is what you can conclude. Now in the next section, next lecture, we will discuss about the situation when E is positive. This was the solution that describes the bound state. In the next lecture, we will see the scattering states. This is for bound state. In the next lecture, we will see what is the solution for the scattering states. And we will reach to very important conclusions. So please watch the videos, like, share and subscribe. That will help you. Thank you.